I want to look at where the formula for the angle between two vectors comes from. But before we do that, there's a little piece of information that we're going to need first. I'm going to look at the dot product of a vector with itself, so u dot u. Well, we can do that by looking at it component-wise. This is u1, u2, dot product with itself, the same thing. When I do the dot product, I'm going to multiply component-wise, so I got u1 times u1. Well, that's not very efficient. I'm going to call that u1 squared, that's better. And then plus u2 times u2, also not very efficient, so that's u2 squared. And you may recognize this. If it had a square root over it, we would call that the magnitude of u. It doesn't have a square root over it, which means it's the magnitude of u without the square root, magnitude of u squared. So the dot product of a vector with itself is equal to the square of its magnitude. And we're going to use that fact in a minute. All right. You may recognize this. It's a nice oblique triangle labeled ABC in the usual way, 3 angles, the opposite sides with the same name. And you may recall from your past the law of cosines, which went something like this. A squared equals b squared plus c squared minus 2bc times the cosine of angle A. Well, I'm going to do that, but we're going to use the vector version of the law of cosines. So let's see. Side A corresponds to vector. It looks like it's going from right to left here, so I'm going to have to call that vector CB. And I'm going to need the magnitude of it. Little a stands for the length of that side. BC or CB is a vector, but if I want the length, that's the magnitude of that vector. So little a squared turns into vector CB, its magnitude squared, equals little b. In this triangle, little b goes from A to C. And again, that's the magnitude, so we get the length of that side. Little c goes from A to B. Minus 2 times, oh boy, little b times little c times the cosine of angle A. Well, okay, we can make this, we can clean this up a little bit. There's a lot of magnitude markings and a lot of A's and B's and C's. Let's see if we can make the notation a little easier. I'm going to name the vector that goes from A to B, I'm going to call that U, just for simplicity. And the one from A to C, I'm going to name V. And then the one that goes from C to B, let's see. If I start at angle A and go to C and then B, I'm adding these two vectors. I'm adding AC plus CB, and the resultant is the vector that goes from A to B. We have better names for some of those things. So from A to C, that's V, plus from C to B, we didn't name that one.
Okay, I found this on the web for AC plus CB, and the resultant is the factor that goes from it to B via better names.
Siri is talking to me, and she really needs to be quiet. I don't know why she's listening into this, but she's done it before, and I'm not very happy with Siri. So we're going to move away from Siri. So we got V plus CB, and the resultant vector is the one that goes from A to B, which we named U. Well, we can do a little rearranging here, just a little algebra, to find that CB I could write as U minus V. Subtracting V from both sides. And so next thing I want to do is rewrite this law of cosines using u's and v's instead of a's and b's and c's. Here it goes. So the magnitude of CB squared I could call the magnitude of u minus v squared. That may not seem like an improvement, but it is eventually. Equals the magnitude of AC, that's v, plus the magnitude of AB, that's u, minus 2 times, this is b, not squared, and magnitude of u, also not squared, times the cosine of a. So we just rewrote the law of cosines again using these other names for a's and b's and c's, using u's and v's instead. My goal here is to solve for cosine of a. That's what I want to get out of all this. Well, this fact that we showed a little while ago, the magnitude of a vector squared is equal to the dot product of that vector with itself. Now's the time for that. I'm going to use that here. Instead of the magnitude of u minus v squared, I can rewrite this as the dot product of u minus v, not u minus u, then it's 0 and we're done. Dot product with itself equals, well, the magnitude of v squared, I can rewrite that as the dot product of v with itself. And same thing for the magnitude of u squared is the magnitude of u dot product with the is the vector u dot product with itself. The rest of these, I'm going to multiplication is commutative, so I can swap u and v. I just feel better if they're in alphabetical order. But we're stuck with those. They're not squared, so I can't make that substitution for the magnitude of u, the magnitude of v. There they are. On the left now, all the usual rules that we expect, things like the commutative property, we can switch the order without changing the results, apply to dot products. So I can multiply out the left side using FOIL or whatever is your favorite way of multiplying binomials with dot products, just like I would if they were numbers. So now I have u dot u minus v dot u, and then minus u dot v, and then looks like plus v dot v. It always gets worse before it gets better, but it's going to be better in a minute, I promise. Equals, no action on the right here, so v dot v plus u dot u plus all this other stuff minus 2, magnitude of u, magnitude of v, times the cosine of a. And hopefully by now you are screaming, there are things we can do. We don't need those dot products with themselves. I have u dot u on the left and u dot u on the right. Why don't we subtract u dot u from both sides? Those are gone. Same thing with v dot v. We don't need those either. Dot products are commutative, so v dot u and u dot v, same thing. So I can combine those and say there's 2 of them. 2 times, or negative 2 actually, u dot v, oh, that's all that's left on that side, equals negative 2 times magnitude of u, magnitude of v, times the cosine of a, and we're actually almost there, because now I have negative 2 both sides. Let's divide both sides of this by negative 2. Goal was to solve for cosine of a. There it is. One thing left to do, and that's divide. We get cosine a equals u dot v over the product of the magnitudes. which is what we were aiming for. And there's our formula for finding the cosine of the angle between two vectors.